Hi, welcome to day 45. Today we're going to take a look at power and electric circuits. I know earlier I indicated we were going to look at batteries, but to tell you the truth, to do power first would actually make more sense. So power today and take a closer look at batteries tomorrow. And today's episode is brought to you by a capital C. Why a capital C? Well, because 1 ampere is equal to 1 coulomb per second. And if you look at those units, that is basically telling you that current is going to be equal to charge divided by time. Don't forget that little fact. It's going to come in handy in about 2 minutes. Okay, so power and electric circuits. First of all, what exactly is power? Well, you might remember from the unit on energy, power is how fast work is done. There's how you calculate it, the work done divided by the time it takes to do the work. And remember what happens when you do work. If I do work on this marker, as I do work on it, I am converting chemical energy in my arm to gravitational potential energy in the pen. If I throw the pen like this, I'm converting, again, chemical energy in my arm to the kinetic energy of the pen. Whenever work is done, some type of energy is being converted to some other type of energy. So you could say power is how fast energy is converted from one form to another. And of course, to calculate your power, well, you take the energy converted and you divide by the time it takes to do the conversion. P is equal to E over T. And of course, when you're dealing with electric circuits, to be perfectly honest, this calculation gets used a lot more than this calculation. All right, so let's take a look at power and electric circuits. Well, before we take a look at a power and actual electric circuit, you know, with a source on one side and a load on another, how about we take a look at our favorite piece of electrical apparatus, a pair of oppositely charged parallel plates. And suppose we take a bunch of little charges, okay, and we do work on them, we drag them from the positive plate down to the negative plate. And let's say it takes us some time t to do that. The potential difference, or the voltage we drag them through, is V. And let's say the total charge of all these little charges is right there, Q. Okay, so you know, I did a bunch of work in some time. How much power am I generating there? Well, power is equal to work divided by time. And remember, if you're talking about charges moving through a potential difference, the work done is equal to the charge multiplied by the potential difference. So this formula turns into this. And I'm pretty sure everyone will agree that what I have here is exactly the same as that. And remember that charge divided by time, how much charge is flowing divided by how long it takes to flow, that's the current, right? Charge divided by time, that's current. So if you want to figure out power, there's how you do it. You take your current and your voltage and you multiply them together. Reserve a few brain cells for that one. Power is equal to voltage times current. The voltage that a bunch of current is moving through. All right, so take a look what we have here. This is a little more familiar with regards to electric circuits, correct? You have a resistance, some current flowing through the resistance, some voltage drop across the resistance, And of course, we know Ohm's law. The voltage across a resistor is equal to the current through it times the resistance itself. All right? So suppose we take this equation and we multiply both sides by I. Okay, nothing the matter with that. Algebra says we can do that. Multiply both sides of this equation by I. Well, look what you have here. The current moving through a voltage, that's power. And what do you have on the other side? Well, I times I is I squared, and then you multiply that by the resistance. There is sometimes a handy-dandy way to figure out the powered electric circuit. I squared times R. Okay, let's have a little more fun with this. Okay. We're gonna start off with exactly the same thing. Ohm's law, the voltage drop across a resistor is equal to the current through it times the resistance itself. Okay. This time though, just because we can, let's multiply both sides by V. Okay, V times V is V squared. Look over here. V times I, that's power, right? The voltage times the current moving through the voltage. Those two things multiplied together, that's power. So you got power multiplied by R. You divide both sides by R. Basically, the R is going to end up over on this side underneath the V squared. And there is another handy-dandy way of calculating power in certain situations. Next thing we'll do is we will take a look at an example where you might have to use one of these ways of figuring out power. Here's a good problem to take a look at. Here's a circuit, and you can see we've got a source that is providing a total potential increase of 10 volts, and we've got a 1 ohm resistance in series with a 4 and 12 ohmer in parallel. And what we want to figure out is how fast the source is producing electrical energy. Now, remember what's going on with the source. If it's a battery, it's taking chemical energy and it's converting it to electrical energy. How fast is it doing that conversion? Well, that's the power of the source, right? And the easiest way to figure out the power of this source is likely like this. Voltage times current. You take the voltage across the source, which is VT, and you multiply by the current through it, which is IT. Now, we know VT is 10 volts. The question is, what's IT? I'm pretty sure we can figure that out, probably using Ohm's law. How about this? How about we say the total potential decrease through all the resistances, that's going to be the same as the increase, right? VT. So the total potential decrease through all the resistances is going to be equal to the current through all the resistances. If you treat this as like one big resistance, well, there's the current through it. Multiplied by all the resistances in total. We'll call that REQ. Okay, so the total potential decrease through all the resistances, VT, is equal to the current through all the resistances times REQ, which is basically all the resistances all totaled up. The question is, what's REQ? What is the resistance of all these things together? Well, take a close look at what we got here. These two things are in parallel, right? The current comes along and it splits and then it gets back together over here. So why don't we call the resistance of these two things R parallel? Let's treat these two things as one big resistance. We're calling R parallel. Now it's a lot simpler. What's this circuit consist of? Well, it's a 1 ohmer in resistance with this one big resistance here, which we're calling R parallel. So the total resistance of the whole circuit is equal to this 1 ohm plus whatever R parallel is. How can we figure out what R parallel is? Well, remember, you can use this formula. 1 over the equivalent resistance of everything in the parallel combination is going to be equal to 1 over the first branch plus 1 over the second branch. So 1 divided by 4, that is a quarter. 1 divided by 12, that's half a 6. Better figure that out on a calculator. 1 divided by 12, that's the same as 0.083. So 0.25 plus 0.083 comes out to that much. So flip this side over, R parallel, and that's going to become R parallel over 1, which is just R parallel. Flip this side over. Okay. Remember, 0.33 is the same as 0.333 over 1. You flip it over, and you get 1 divided by 0.33, which is the same as 1 divided by a third. So that is going to be 3. So R parallel is equal to 3 ohms. R parallel is equal to 3 ohms. I'm going to write that down here so I don't forget it. So the equivalent resistance of everything is going to be, well, 1 plus 3, which is equal to 4 ohms. So now I can come over here. Hey, my total voltage decrease, same as the increase, 10 volts. The current, that's what I'm trying to figure out. Req is 4. You solve this equation, the 4 goes over to the other side and goes downstairs, and you get 2.5 amps. So our current is 2.5 amps. Now we know the power of the source, how fast the source is producing electrical energy. 10 times 2.5, which is going to be 25. And don't forget, power is measured in watts, which is the same as joules per second. All right, good enough. Let's do part B to this question now. All right, let's see if we can figure out how fast the parallel combination is using electrical energy. So these two things here together in combination, how fast are they using electrical energy? Well, remember what's going on with them. They're taking electrical energy and they're converting it to heat energy. How fast they're using the electrical energy, how fast they're doing that conversion, that is the power of these two things. So essentially we're figuring out the power of the parallel combination. Now remember, there's 3 ways to figure out power. You can go V times I, you can go I squared times R, you can go V squared over R. Which should be easiest in this case? Well, we don't know the voltage across the parallel combination, right? We don't know the voltage drop across the parallel combination. We know the voltage drop across everything is 10 volts, but the voltage drop across the parallel combination, okay, we have no idea what that is, so I'm not going to use these two. Do I know the current through the parallel combination? Well, yeah, take a look. If you treat this as one big resistance, what's the current through it? The current through it is the total current in the circuit, which I figured out when I was doing the last question, 2.5 amps. So how about this? The power of the parallel combination is going to be I squared R. We want the current through the parallel combination. And again, if you treat this as one big resistance, there's the current that's going through it, 2.5 amps. And again, if we want the power of the parallel combination, we need over here the resistance of the parallel combination. And we know the total resistance of these two things, we worked that out last time, that is going to be 3 ohms. Yeah, so the key when you're doing these power calculations is make sure all 3 variables, make sure they all pertain to the same thing. If you're talking about the power of the parallel combination, this has to be the current through it, which it is in this case 2.5. This has to be the resistance of it. And that, of course, is what we're after here, the 3 ohms. Okay, so you do this calculation, and what do you get? 2.5 squared times 3, that works out to 18.75 watts. Okay, let's see if we can do this next one. How fast all the resistors are producing heat energy. Okay. You know what? You can probably do this without any calculation whatsoever. Everything you calculated, you actually calculated before. Think about this. Okay. The source is producing electrical energy, and all the resistors are taking that electrical energy and they're turning it into heat energy. So however fast the source is producing electrical energy, that's how fast the resistors are producing heat energy. In other words, how fast the resistors are producing heat energy? Well, that's we'll call that the power of all the resistors. Well, that's going to be equal to the power of the source. Okay, agreed? How fast the resistors are producing heat energy? Well, that's going to be equal to how fast the source is producing electrical energy. Because let's face it, any electrical energy the source produces, well, the resistors, they end up producing heat energy with that. Okay? So the power of the source, how fast it's producing electrical energy, that's how fast the resistors are producing heat energy. That's the power of the resistors. And we did that calculation already. The power of the source is 25 watts. Okay, still not quite done this. We want to take a look at another couple things in just a bit. Let's take a look at this one now. How much heat energy does the 1 ohmer produce in 1 minute? Well, if we want to figure out how much heat energy it produces in 1 minute, we're going to need to know how fast it's producing heat energy. First thing we're going to have to figure out is the power of that 1 ohm resistor. How can we do that? A couple different ways. How about this? All the resistors are producing heat energy at the rate of 25 joules per second, or 25 watts. These two, they're producing heat energy at the rate of 18.75 joules per second, or 18.75 watts. So how fast is this one producing heat energy? Well, how about this? You take how fast they're all producing heat energy, 25, and you subtract away how fast these ones are producing heat energy. And there's your answer. I think that comes out to 6¼ watts. And if you want to check your work, how about this? We could say, well, the power of the 1 ohm resistor, how can we figure that out another way? We could use this equation. We could use this equation. We could use this equation. Which equation would be easiest? Well, I don't know the voltage across this 1 ohmer, so those two are out. I don't know the current through it, it's 2.5. So yeah, how about we do this? The power of the 1 ohmer, that's going to be the current through it squared times the resistance itself, so that's going to be 2.5 squared times 1, and you do 2.5 squared on your calculator, and it had better come out to 6.25. And yeah, it does. And that's the thing about these circuit questions is lots of times, almost every single time, you can figure out one thing 2 different ways. I encourage you to do that. At least some of the time, make sure you get the right answer. All right, we are almost done this problem. We're going to come back and do the last part. All right, time for the last part of this problem. We want to calculate the power output of the 4 ohmer using V squared over R. So the power of the 4 ohmer is equal to V squared over R. Well, if we want the power of the 4 ohmer, that means we need the voltage across it. We'll call that V4. And of course, we're going to have to use its resistance. So that R is going to be 4 ohms. The question is, what is the voltage across this resistor? How can we do that? Well, how about this? I can calculate the voltage across this resistor pretty easy, right? Call that V1. The voltage across this resistor is equal to the current through it, which is 2.5, times the resistance itself, which is 1. So the voltage across this resistor is equal to 2.5 volts. And remember, in any circuit, the voltage increase is equal to the voltage decrease. So if you're an electron, again, don't see one big circuit here. What I want you to see is 2 circuits. If you're an electron, you can travel around this circuit, or you can travel around this circuit. So let's suppose we're an electron and we're traveling around this circuit. You got an increase of 10, that means you got a decrease of 10. If you gain 10 here, that means you got to lose 10 in total. If you're losing 2.5 here, when you come around here, you got to be losing, well, 10 take away 2.5. So this voltage right here, it's going to be the difference between 10 and 2.5, 7.5 volts. Everybody agree with that? If you're an electron, you're going around this circuit, if you gain 10 volts here, that means you got to lose 10 in total. 2.5 through this resistor and 7.5 through this resistor. And, well, now the power of the 4 ohmer, well, that's a piece of cake. It's going to be 7.5 squared divided by 4. Whatever that turns out to be. Better be less than 18.75, right? Remember, these 2 things together, their power together was 18.75, so this better be less than 18.75. Okay, let's see what it comes out to. 7.5 squared divided by 4. Yeah, it comes out to, round it off, 14.1 watts, done. Okay, tell you what, just before we leave this one alone, just for the heck of it, suppose we figure out, again, just for the heck of it, suppose we figure out this voltage some other way. Just giving you a little practice here solving circuits in general. So let's see if you can figure out this voltage some other way. How about this? Suppose if I treat this as one big resistor, okay, and we're pretending we don't know what that is right now. If we treat this as one big resistor, as I go from here to here, I'm going to lose a certain number of volts. Doesn't matter whether I go through this branch or this branch, so I go from here to here, I'm going to lose a certain number of volts. So how about we say the potential decrease across this one big resistor, we'll call that V parallel, is going to equal to the current through this one big resistor. And if you treat this as one big resistor, the current through it is 2.5 amps. And yeah, the voltage across the resistor is equal to the current through it times the resistor itself, the resistance of this one big resistor. If you treat these two things as one big resistor, their combined resistance is 3 ohms. And yeah, 3 times 2.5 is 7.5 volts. If you treat this as one big resistor, as you go from one side to the other, you lose 7.5 volts. You lose 7.5 volts going through the 4 ohmer, and of course, you'd also lose 7.5 volts going through the 12 ohmer. Okay. So just a little extra practice there in applying Ohm's law and solving circuits. Regardless, so hopefully now you're pretty familiar, probably more familiar than you want to be with when it comes to figuring out power and electric circuits. There will be an assignment posted that'll give you some practice through this. Make sure you work your way through it, and working through that assignment will definitely help cement all this stuff inside your minds. And tomorrow we will take a look at batteries in more detail, specifically why the voltage output of a battery drops when it's supplying a current to something. We will see you then.